Hello. Uh, Previously, in the first section of this lecture, lecture 5a, we discussed about analysis of variance, and also we mainly focus on one way ANOVA when we have only one factor, and that one factor has many levels. Remember examples like drug. Drug is one factor, but there are different levels of drugs, like different types of drugs, right? But in reality, it also happens that you have more than one factor at the same time, and more than one factors, and both of like if there are two factors, for instance, and then they all have they do have different levels as well, right? Factors with levels. So what do we do when we have a situation like that? For instance, you have drugs at three different levels, and also you have a diet plan, for instance, at three different levels. And those two factors, like diet factor and the drug factor, they were employed on patients. So now you have two factors, drug and diet, and patient is my main subject to study, right? I am applying both of those levels factors on my patients, and my drug has three levels and my diet has three levels as well. So what do we do? How can we evaluate situation like that? And how can we see that whether they are differing one another or not? Do we have any impact? Do we see any impact when we apply drugs at different levels on patient, and also also the diet plan at different level on patient? Do we see any difference on that? So in situation like that, we go for like two-way ANOVA. Well, it says two-way ANOVA, but it can have more than two factors, for instance. I said more than one factor, right? So for instance, as I explained here, the drug example, we have two factors. So the one famous idea is the blocking principle. And the blocking is a technique for dealing with the nuisance factor, right? So the nuisance factor is a factor that probably has some effect on the response. So response is patient, things like that. But it is of no interest to the experimenter, however. The variability it transmits to the response needs to be minimized. Now think again. Consider the same example. I have a patient, and patient was investigated with respect to factor number one, which was drug, right, at three different levels, but also with factor number two, which was diet, at three different levels, right? Now you have two factors, and your response is your patient. Now, very important, I need your attention here. You have two factors at different levels, and you were applying those factors on the response, which was your patient. But you are only interested in investigating one of the factors, not both. If you are only interested in one of the factors, not both, so the one in which you are not interested in, you can put them in block. So this is what the blocking principle says. You block that principle, that factor. For instance, if you want to know the effect of drugs on patient, then you will block diet. If you wanted to know the effect of diet on patient, then you block the drug. Why? Because both of them are implementing on patients. So you need to have you need to block one of the factors so that its effect can be minimized. Read it here. The variability transmit to the response need to be minimized. We don't want that variable which we are not interested in to influence our results, and that's why we need to block them. So one idea is that if you have more than one factor, and if you want to evaluate one factor at a time, not all of them, then you block the others. This is the simple idea. For example, an experiment is designed to test a new drug on patients. There are two levels of treatments, drug and placebo, administered to male and female patients, right? Now here, the sex is another factor. In this example, sex is another factor, like male and female factors. So the sex of patient is a blocking factor, accounting for treatment variability between males and females, because I'm not interested to know whether what type of drugs were implemented, or how female or male, and if males are behaving with respect to drugs. I wanted to know how patients in general are behaving with respect to drugs. So I blocked the factor which was the gender factor, which was the male and female sex factor, right? Typical noise sense factor include batch of raw materials, what kind of batches you have for the raw materials, operators, pieces of test equipment, and time, like day and night shifts for producing uh, uh, particular product, for instance. So since we are not interested in those factors, we block them, right? And we consider or we focus more on the factors which are more interested to us. If the noise sense factor is known and controllable, blocking can be used to eliminate its effect on the experiment result, right? Like if for the gender of the patient's case, we know the factor and we can control them, well, we can block. If the noise sense factor is unknown and uncontrollable, then we do not know the factor exists and it may have some influence on the experiment. Sometimes you don't know what are the factors actually somehow affecting the whole experiment. So what we do, we randomize the design, which can be used to guard against such factors. And by randomization means we draw randomly many observations, and we draw this randomly. Remember this idea of randomness when we discussed earlier, that when we draw randomly, it means we can if there are some peculiar values, we can somehow eliminate them through randomization. The third category is if the nuisance factor is known but uncontrollable. You know something but you can't control, like temperature, right? Somehow you don't know how to control the temperature of the environment, of the laboratory, for instance, or the experimental unit, for instance. So the analysis of covariance can be used to compensate that. By the way, we are not going to discuss this in this course, but this is one way of the one way to solve this problem actually. And failure to block is a common flaw in designing an experiment. We should be familiar with what kind of factors we need to block, right? And accordingly we can pick strategies or methods, for instance. So blocking and nuisance factors. So the randomized complete block design, or RCBD, is the famous design or method which we use when we do for blocking. So you don't need to like think too much about the terminologies, but for some of you who are interested in learning quantitative methods in detail, for instance, they may get in touch with those methods. If you Google them, you will find more details about that. So for example, the hardness testing example, we wish to determine whether four different tips, I said last week also, read and mark the words. Use pen and paper and then mark over there what you are actually reading. So you have four different tips. It means you have four levels of something, right? Different hardness, right? So you have four levels of hardness. Reading on a Rockwell hardness tester. Assignment of the tips to an experimental unit, that is a test coupon. One can consider a completely randomized experiment like the previous one we discussed in the previous part of this video, like in 5A, when we were dealing with one-way ANOVA. But the test coupons are a source of nuisance variability. They can have variation as well. So alternatively, the experimenter may want to test the tips across coupons of various hardness level, and there we need a blocking. So we need to block the test coupons in order to test the tips across coupons. So to conduct this experiment, and we know that the design which we need is randomized completely block design, since we are blocking one of the factors which we are not interested in. So it assigns all four tips to each coupon, and each coupon is called block. So coupons are blocked. That is, it is more homogeneous experimental unit on which to test the tips. So variability between blocks can be large, and variability within a block should be relatively small, right? This is the idea. So in general, a block is a specific level of a nuisance factor, like the factor which we are not interested in, for instance. So we run this design in a randomized manner, and these are the values. So and here you see the randomization. So you have test coupons which were blocks, and there are four tips 1, 2, 3, 4, and you see that since those test coupons were 4, there were 4 levels of tips. But now there is a randomization. So I somehow draw tip number 3 first, and then tip number 1, 4, and 2. In the second case, I draw 3 first, and then 4, and 2, and 1. So you see, there is no pattern over here. At least there is no pattern in terms of sequence, and that's how we randomized it in an experiment. Well, when you construct a design, when you run an experiment, you do these things. But sometimes you don't do these things, but you get a data in that manner, and you proceed for the next level. Now notice here the two-way structure, like dependence in among the tips and also among among the test coupons as well. So once again, we are interested in testing the equality of treatment means, but now we have to remove the variability associated with the blocks, right? That is the variability we need to eliminate. So this is the design. Recall equation number 1. There we had mu, alpha, mu, and epsilon. Now we have another factor beta, which is for the blocking factor, right? And since we are not interested in blocking factor, our null hypothesis is also only dealing with mu, the test levels. So we are interested in testing the equality of treatment means, but now we have to remove the variability associated with the nuisance factor. And how can we do that? Well, so this is the design, this is the structure, mathematical structure of the formulas. So we divide the total variation SST, the sum of squares of total, with respect to sum of squares of level in tips, sum of square of blocks, like coupon blocks, and some part from the error. Right? So if you sum these terms together, you will get this value. So somehow the total value, the total variation is decomposed into 3 different components. So we plug in values over here and then we get the final value. But in SPSS, you don't do that, right? You only get the final result and then you compare your result with respect to your p-value or with respect to alpha, right? But this is the classical output. So if you want, you can somehow spend some time thinking about this table, but if not, you just skip that. So suppose that there are A treatments and B blocks. So treatment means are equal. It means this will be the hypothesis, like means are related as treatments are related as mu1 and mu A. And since we have B blocks, for instance, so the blocks can be, if we are interested in, we can even test blocks. Beta 1 to beta 2, they are equal or they are not equal. Again, some formulas for those guys which we saw in the table, but again, you don't need to remember those formulas. So now let's look at the example. By the way, this is an example I copied from one of the very famous books on focusing on ANOVA. So I would like you to read this example in detail and also the output and discussion, which is available in the next page. So now in this experiment, we have, well, the PSI, the pressure level, 4 pressure level, and then there are 6 blocks, right? And these are the values, right? So we plug in values into those formulas, and now there's a discussion going on here about the final output, final analysis, final, so to say, final conclusion. Remember, our test hypothesis is that all the means are equal and all the blocks are equal, right? Now we will compare our p-value with alpha and see whether are we going to reject or not reject. So now here the p-value is very low, 0.001. And our alpha was 0.5%. Here, alpha equals to 0.5%. So we compare our p-value with alpha and we decide that we are going to reject our hypothesis. And the treatment means are different, right? By the way, you see only one p-value over here associated with treatments because these are the blocks. We are not interested in those blocks. We don't want to test them, right? We are only interested in treatments. So there is only one p-value associated with this guy. And since p-value is less than alpha, so we reject and say that all the treatments are different, standard. This will be the incorrect analysis. For instance, if I do not block, so here I blocked my badges, but if I ignore the blocks, this will be my answer. But this is an incorrect analysis. And you see that the p-value is even bigger. Right now it was very lower over here, but now it's a bit bigger. So at 1% I can't reject because p-value is greater than 1%. But at 5% I do reject. But in general, this idea is not good because I had some factors which were influencing or which could be influencing on my experiment, so I needed to block them. So if I do so, I'm running a experiment correctly. But if I don't do so, then it means that my experiment was not done properly. We do some residual analysis as we discussed earlier. Some plots. Over here is the normality. It means the residuals are normal. It says that there is no structure. I don't see any pattern over here. So it means my model is acceptable. Some other graphs related to residuals. So conclusion is that both residual plots indicate that normality and constant variance assumption are satisfied. No obvious problem with randomization. No pattern in blocks in residuals versus blocks. Like residuals were not associated with blocks. They were not depending on one another. And also the residuals were not associated with pressure, the other factor. So they were not depending on one another. So if we see that there are no patterns like that, it means we say that, okay, our model is good. We can consider that model. And if we consider that model, it means we can rely on our conclusion. We can even go for like testing for means, as we discussed previously, multiple comparisons, for instance. Now you have 4 levels and we can compare them in pair, like 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. And now you see something very interesting, which we couldn't see earlier in the previous example, in the previous part of this video, of this lecture 5a. There, all of the p-values were actually less than alpha. And we say that, okay, all of them are different. But now it's very interesting here. It says that the first and second treatments, they are not significantly different. Because here we can't reject our hypothesis. Here the p-value is much bigger than alpha. For 1 and 3, well, we can reject at 5% level, but we cannot reject at 1% level, right? Here we can reject significantly at both 5 and 1%. Here we cannot reject at 5 and 1% both. Here we can reject, here we can't reject. So it means that 1 and 2 are not significantly different, 2 and 3 are not different, and 3 and 4 are not different, but others are different. So sometimes you see that by doing this pair analysis, sometimes you see that some of the pairs are really different, some of them are not different. So this somehow let us dig in to the whole analysis, because initially we concluded all of them are different, but we wanted to know which one of them are more different and which one of them are less different. And that's what we do through this method, the least significance difference test. Factorial experiment. We move on further a bit to a bit more complicated method. Sometimes we have 2 factors, as I discussed earlier. Recall the example again. Patients were the response, and we had drugs as one factor and diet as the another factor, right? And both of those factors has different levels. But now I am not only interested in one factor, rather I am interested in both of the factors. Because if you have more than 2 factors and you're only interested in one factor, then you will use the blocking strategy. But now I am interested in both of the factors altogether. So that's what we call as the 2-factor factorial or 2-factor method, so to say, right? Which is an extension of the more than 2-factor model we saw earlier. So here is that. Since we have 2 factors, factor 1 and factor 2, and both are like at low and high level, and factor B is also low at high level. So we wanted to see if are they related to one another or not. If they're not related to one another, it means that there is no interaction between them. Right? They're not interacting with one another. And in a classical mathematical way, their plots should look like these, like they are like 2 separate lines. There is no connection between them. I don't want to talk more about these values. If you want, you can even think, but they're not too important. You need to know the concept at least. But sometimes there is a connection. Sometimes there is a dependence like here. So B positive, like factor A and response, so they are somehow connecting with one another. It means those 2 factors have something in common. They at some point they commonly apply to the response. They commonly influence the response. Diet and drug, Somehow they are commonly participating to treat the patient for instance. So this information is very important. If they are like connecting with one another, we say that there is some interaction, there is some dependence between factors. And if we know that there is a dependence in factor, then we should incorporate them in model. This is very essential. So like here in this example, you have three type of materials, 1, 2 and 3, and you have three type of temperature, 15, 70 and 125. And at each level we had four values, like at each of both levels, like temperature, when temperature was 15 degree Fahrenheit, and when type was 1 we gathered 4 data. When temperature was 15 and type was 2, we gathered another 4 data, 4 observations, and then we keep doing this until we are done with the experiment, with the data collection. So here factor number A is material type, factor number B is the temperature, right? The quantitative variable, by the way. So what effect do material type and temperature have on the life of the battery? We wanted to evaluate the life of a battery, but life of a battery can be influenced by different factors like temperature and material type, right? And both of those factors, they have different levels. So how do we evaluate this hypothesis? What effect do the material type and temperature both have on the battery life? So well, this is a mathematical structure. Again, you don't need to remember those formulas. But here, look here in the statistical model. So alpha is constant, mu is the guy for the treatment or one factor, for instance, factor number 1, and beta is the guy for the another factor. So like mu, if I say mu is the material type and beta is the temperature. But here, the mu and beta all together, this is the interaction. This allows me to account for interaction in the data. And I will see, when I will test this hypothesis, I will see, are there any interaction in the data or not, or are there any interaction in the factors or not, right? So but in order to, well, we always need to account for interaction if there is an interaction. If we don't do that, it means we are in a trouble. Our design may not give us a good result. So we move on further, and again, you don't need to remember those formulas, but I see that some of them are horrible, but that's how the total variation of is decomposed with respect to treatment number A, or factor number A with respect to factor number B, some interaction part, and then error. So if we summed up together, we get the total variation. So here are the results. So material types, temperature, interaction, error, and total. If you summed up all four values, you will get the final value. Now look here, the p-value. So you have three p-values here, not only one p-value, because we are interested in all of the factors altogether. So we run a different model. And we will run in SPSS how can we choose different models, how can we choose different type of ANOVA. So for material types, the p-value is much less than alpha. It means all of the material types are not same. It means all of them are influencing the battery life differently, right? We reject our hypothesis. For temperature, again, we reject our hypothesis and we say that yes, temperature do have some impact on the battery life. The temperatures are not same with respect to battery life. Interaction, yeah, here the p-value is less than 5%. So it means at 5% level of significance, yes, there is an interaction. So in the hypothesis was, by the way, note very attentively here, the hypothesis, the null hypothesis here was there is no interaction. It means, well, because we are interested in knowing the interaction or not interaction, so the null hypothesis was no interaction, and alternative was yes, there is an interaction. So we reject a hypothesis and say that yes, there is an interaction because this value is less than 5%. If I'm going to compare all of them at 5% level of significance. We go for residual analysis. We check for residual plots like normality and structure in order to say that, in order to see whether are we going to rely on our result or not. Some residual analysis with respect to material type, because material type was one of the factor, and also with respect to temperature to see are they do they have any kind of any dependence or not with respect to them. So That was the idea. So remember, you have more than two factors, but sometimes you're only interested in one factor, not the other. So you block the other factor. That was the first part of this video. But sometimes you have more than two factors and you wanted to evaluate them together. So this is this part of this video. In reality, you can have even more factors, like k factors. For instance, like here. So you have factor number A, factor number B, then factor number C, up to so on. And then their interactions like with AB, with AC, and then like interaction with more than two factors, like with A, B, and C. Since you have more than three or more than five factors, for instance, you can even consider them in a similar manner. So this will be, for instance, if I have three factors only, then this will be my table. So factor number A, B, and C, then interaction between factor A and B, interaction between factor A and C, interaction between A, B, and C, and the interaction between all of them together, like A, B, and C, and error, and then total. And that's how we can evaluate. Here are the values. We get the p-values to see, are we going to reject factor A, B, C? Are there any interaction between A and B or not? Between A and C, between B and C, and between A, B, and C altogether. So these values we are mainly interested in because they will help us to decide, are we going to reject corresponding hypothesis, null hypothesis, or not? Right? So it's another example. A soft drink bottler is interested in obtaining more uniform fill heights in the bottles. So the process engineer can control three variables during the filling process: the percentage carbonation, operating pressure, and the line speed. So there are three factors: how many carbonation involved in the filling of a bottle, the pressure, how much is the pressure, and also the line speed. And we have different levels of these factors. For instance, for the carbonation level, we have three factors: 10, 12, and 14%. For the pressure, we have two levels, which is 25 and 30 psi. And for line speed, we have two levels, 200 and 250. So now we have three factors, but all of them have different levels. And we wanted to compare their performance on the soft bottle filling height. So here is the data. And now you have, well, by the way, notice that we have two observations at each level of factor number one right here, like 20. So operating pressure was like 25 and 30, and then at 20, again you have at that particular pressure level you have two speeds, both of them 200 and 250, 200 and 250 over here as well, and then percentage of carbonation. So we have data like that in this table, and then we move on to apply the method. So now here three factors individually, and then their interactions, and then finally the total. Here are the p-values. So the first two p-values says that the percentage of carbonation and operating pressure, of course, they are much less than 0.05. This guy is also less than 0.05. It means all of them, they are not behaving similarly with respect to the filling height, which they should be. Interaction, of course, there is, well, we say that, okay, there is no interaction. We do not, we see that we do not reject our hypothesis here because it's at the border of 0.05. So we accept that. Of course, we accept here as well, we accept here as well, and then here as well. So it means all of those factors, they didn't have interaction, but individually they were behaving differently, right? Another example, which you can read even in a more general way. So we have three different factors: gap, gas flow, and power, and there are some interactions associated with them. We run the whole experiment, and then we get the p-value. And the p-value says that the gap, yes, it was performing differently with respect to levels, but gas flow was not performing differently. We couldn't see a significant difference at different level of gas flow. Power, yes, it was significantly behaving differently with respect to levels. There was no interaction between gap and gas flow. There was no interaction between power and gas flow, but there is an interaction between gap and power. Yes, here we reject our null hypothesis of no interaction. So the basic ANOVA procedure treats every factor as if they were qualitative. Sometime an experiment will involve both quantitative and qualitative factors, and this can be accounted in the analysis to produce models. For instance, I say regression models. We consider all of these models as regression models, and sometimes we go for response surface curves or response surface to interpret those results. We are not going to discuss them in detail, but I wanted to give you a clue that if you move on further, like extend your analysis, then you can resort to those methods. So today we learned about one-way factor, one-way ANOVA, when we have only one factor and we wanted to evaluate, well, that factor has many levels, and we wanted to evaluate whether that factor at different levels influence the response or not, right? So that was the one-way ANOVA. The second part was the two-way ANOVA, but in the two-way ANOVA, when we have more than one factors, and so the first part was when we have more than one factors, but we are only interested in one factor, not the others, right? So we block them and then study the one factor. So that was the blocking part. The second part was the two-way ANOVA or the two-factor experiment, when we have, say, two factors influencing the response at different levels, and we wanted to evaluate both of them altogether. So we consider them simultaneously and consider and design them in a two-factor model. We can have, of course, more factors in reality. So these are the methods we learned today, and they will be we will be utilizing them in assignment number 2. Of course, we will be investigating them with our data through SPSS. So please read the notes and also listen to the lectures. If you have questions, you can even ask in seminars. Wish you good luck with respect to this topic. It's not too difficult. Try to understand. Keep the basic idea intact in your mind about like one factor or two factor method, and then pick a suitable model, and then finally, we compare p-value with alpha and then decide, are we going to reject or not. Thank you very much.